Hello. Hey. I, I will say that we need to start, otherwise, yeah, Ronnie will not have enough time to show his VR stuff. That is super cool. So wait. I am loud enough so everybody can hear me in the back. Good. Yeah, because I will do that because I need to move. So. Um, I'm going to talk today about how to test the test. So I'm going to talk about Mutalk, which is a project that started a long time ago. I will give a bit of history for those interested. But so, in the continuation of last year, so those that were there last year in ISOG, I was presenting some techniques of fuzzing to generate automatically tests, using grammars and stuff like that. And the question is, okay, I can generate tests automatically. I can generate thousands of tests. And the question is, okay, how good are them? Yeah, maybe they are redundant. Maybe they are not good enough. They are not testing the right part of the application. So a Mutalk kind of gets on how to answer that question. Yeah. So just for those that don't know me, I don't have my name here. So okay, Guiche. I am Guiche. So I will actually change this slide to put the phonetics because that's always a problem. So I work here upstairs in the third floor as a researcher. I work in compilers, testing, and stuff like that. I do some Japanese studying. So just for those that don't know me. And I'm here to talk about tests. So, okay, everybody knows, so this is a test. So everybody who didn't ever write a test? Okay, so we can talk later. I want to show you how to write tests. Okay, good. I identified the person, the target. So, okay, but the test, okay, I don't care about this too much. So we want to test here a set. And this set, we want to add stuff on the set. And we do assertions to check that it satisfies some conditions. And we love to write tests. Everybody here loves it, except the ones that never wrote any test. But you will love them. Because actually, you have your application, you run the tests, and then you have either green test, and we love the green color, that says that your application is healthy, it's good. And if you have tests that are red or yellow, but okay, something is broken. Either the tests are bad or your application is wrong, but something is messed up. Yeah, and we use this to measure somehow the health of our applications. Now, we can ask ourselves, what happens if we have a bug in here, right? Because we are humans, we make mistakes, and okay, maybe the tests are not so infallible, right? So, and then, okay, what is a good test? We can have many definitions, probably as many people we have here. So this is my definition. A good test is a test that catches a potential bug in the future, right? So it works more like a regression test. Now, of course, given this question, we can say, okay, how can I build a tool to watch the test, right? To say, okay, these tests are good or not, right? And we need to somehow say, okay, this test catches bugs, this test doesn't catch bugs, eventually in the future. So, okay, we can it's kind of a vigilante thing. Where we can say, okay, this decision is probably a bit arbitrary. So, who takes the decision of what are the good tests? We have a tool that is our vigilante, and I will tell you a bit how it works. So it's called Mutalk. That is actually, it was not originally developed by me. It was developed in 401.1, like in 2009 at least, so 15 years ago. It has passed around many hands. So Pavel, for example, migrated it from Smalltalk Hub maybe or something like that to GitHub at some point. And in the last 6 months, we have done a lot of improvements. It is working between 409 and 412 right now. So if you want to use it, you are welcome. What is the idea behind this tool in one slide? Is that if you give me your application and your tests, so you can, for example, compute code coverage. And you can say, OK, I have this project artifact that is a PDF generator. And it says, OK, yes, I have 30% of code coverage. It's a good coverage. Maybe not, but it's It's maybe 30%. It's a bit stronger. It's a bit strong there. But if you measure this with Mutalk, it says, OK, no, you're actually 4% good only, which is not so good. You want to be closer to 100%, right? So that is the key of this tool. It will evaluate several things and tell you, OK, it will give you a score and say, OK, your tests are this good. Yes, and this is not good. So how does it work? The main idea is that you take your application, you take the test that you wrote for that application, and then you create mutants. Yes, I will show you how the mutants look like. It's not like that, but and then given those mutants, we compute the score, this score that I showed you. So, and of course, if we have a high score, we say yes, you are good. Your tests are good. They kind of you have tests that actually are resilient and they can kill the mutants. I will show you later. Or if you have a low score, then you need to improve your test somehow. Yes. Of course, when I'm talking about mutants, I'm not talking about this kind of mutants or this other kind of mutants. I'm talking more about this kind of mutants. Yes. So what we're going to do is to introduce artificial bugs in your application automatically, and to see if the test detect the bug. Yes. So what I was saying before is, OK, a test is good if it detects a bug. So if I can introduce a bug, and my tests detect that, that means that my tests are accounting for that potential change, which is something I don't know if you do it. Probably if you do TDD or so. Something that happens to me all the time is that when sometimes I do a feature or I fix a bug without doing this technique, this automated technique, and I fix a bug and then I write the test afterwards. Yes, that's something that happens. So you write the test after having the fix. But how do you know if the test is working or not? Well, what I do is I manually undo the fix to see if my test that I wrote afterwards now actually detects the failure. And if that happens, then I put back the fix, and I'm happy. I make my pull request, and everything goes forward. So the idea of this tool is to automate and to systematize that practice, right? Now, we can ask ourselves, what kind of bugs are we going to introduce? And this is something, it comes from some research in the 70s. Yeah, so but it's based on some idea that is called the competent developer hypothesis, that says that you and me, so everybody here in the room, we are all smart. We know what we are doing. Yeah, so when we make mistakes, when we put a bug there, it's not that we do it on purpose or we do really difficult, really gross, I don't know, complex bugs. Most of the bugs that we're going to introduce in an application are really silly things, like, I don't know, an inverted condition and you miss the if true by default in some case, or you are missing a plus or a -1 in a loop and then you have a stack or a buffer overflow at some point. I don't know, but those silly things that we need at some point to detect, right? But of course, we are going to make mistakes because we have to manage applications that are thousands or hundreds of thousands, maybe millions of lines of code. OK, we kind of can manage only a couple of abstractions at a time. So we're going to make mistakes. And of course, if I give you Mutalk, what is going to happen is that it's going to create thousands of these simple mutations. Yes, like for example, here we see one where I'm going to replace this condition by false to make it always go to through this branch, right? So if you have a test that actually had to go this way, that test should fail, right? So at the end, what we do is we do control flow bugs, we introduce arithmetic bugs, we introduce logic bugs, overflow bugs, typos, and stuff like that. So it's really simple in the idea. And it creates, for example, here I don't remember which is the project I was running. This is in Microdown, and it created 3,000 mutants. Yeah, so 3,000 variations of the code that have bugs, 3,000 buggy versions of your application, right? And OK, once we have these mutations, what we do is we do the so-called mutation analysis. So we take the application, we apply the mutation. So we change one little piece of code. That creates a mutant. We run all the tests. And then if all your tests are green, that means that no test detected the mutation. Yes, so if all your tests were green, you introduce a bug, and the tests are still green, that means that, hey, wait, this went there inside and you didn't see it. So we say that the mutant survived. And if there is at least one test that is red, that means that at least one test detected the mutant, so we say that it was killed. And this is, you can think about it like a game, so we want to kill as much mutants as possible, right? What is the insight behind this? So we have these surviving and killed mutants. When you have a surviving mutant, it's either because you have some code that was mutated that is not covered. Yeah, you can, for example, increasing coverage is one way to increase mutations. Maybe the code is covered, but you were not asserting something that was important. Sometimes we have, I will not go in here because this is mostly a research concern, but sometimes the mutations are equivalent. Like if you change the plus by a minus, but B is always 0, then actually these two are equivalent, and they don't change. So that can bias a bit the results. But at the end, we have these survived mutants and these killed mutants, and the survived mutants, they are hinting us, okay, how can we improve our test? What are the tests that we need to write to have a better coverage of the application? And at the end, we compute the score like this. It's just a ratio of killed mutants against all the total mutants. So pretty easy, straightforward. And yeah, OK, so far so good. We have this. And Mutalk had this since its beginning. So the version of 2009, it was OK. But the thing is that there's a big problem with this approach in general, which is that it takes a lot of time to run. So the biggest your set of tests and the biggest your application, the biggest the time this mutation analysis works. Because as I tell you before, you need to apply a mutation and then you run all your tests to see if the test killed the mutant or not. So that means that for every mutant you need to run all the tests, and if the tests take a lot of time to run and you have a lot of mutants, well, that makes a pretty big runtime. So one of the main concerns, and that is kind of one of the improvements that we have done in the last 6 months, is to see how can we improve the runtime to make it practical so everybody here in the community can use it. And there are two main ideas, really simple. So how can we run less tests and how can we have less mutants? Because if we reduce either of them, then we're going to have something that runs faster. Yeah? Of course, we want to not impact too much the score, because if you make it faster, but then the score, it doesn't represent the score of the 100% analysis, then it's kind of useless. So the first thing that were there since 2009, so we had already some strategies to cope with this. It was based on code coverage. Yes. So if you know the code coverage of each test, so for example, the test 1 covers the two mutants on the top. The test in the middle, the test 2, is covering these two mutants here. And the last one is covering this one. And this one is not covered by any test, right? We can think already about some optimizations that were already there before. Like, OK, we can run, every time that I want to evaluate a mutant, I can run only the tests that cover the mutant. And I don't need to run all the tests. So for example, when I am going to evaluate this mutant, and I want to know if it survives or gets killed, then I can just run this one. However, no, sorry, I can run this one and the green one, yeah, because it's covered by the blue and the green. On the top, if I have the top one, I only need to run the first test, yes, and that is enough to know if the mutant survives or not. On the same venue, I can only we can not create the mutations for the code that is not covered, yeah, and that kind of also saves time during the mutant generation phase. So. Still with this approach, there is a lot of mutations that remain. So what else can we do? And one of the ideas that have been there in research in the last years, and we have implemented in the framework because they work well, is to use random sampling. Yeah, we just take, OK, I have a pool of thousands of mutants, but what if I take 10% at random, yeah, or 20% at random? How does it change the mutation score? So the idea is if I take just 10% of the mutants, then I will take this will run 10% of the full runtime, so it will be 10 times faster. Here what we see is, for example, this is a little experiment just to show it here in the conference. I ran Mutalk on Pharo's UID implementation. And here what we see is the percentage of sampling. So here I am sampling 5%, 10%, 15% of mutants. So we see how I take more mutants and the mutation score actually goes up. So here what we see is that at some point it kind of stabilizes between 60 and 70%. Since it is random, of course, it's not deterministic. But here what we can see is that if we take 30% of the mutants, we have already a good enough score. So actually I can run 30% of the mutants only, and that kind of will suit our application. So of course, it could happen that the random sampling is not good enough for your application, because maybe if you have, for example, some big classes that have a lot of code and a lot of small classes that have very few code, it could happen that the random sampling will always sample from the big class, the big method that have a lot of code. So some other strategies that we have developed were guiding the random sampling using some stratified sampling. So the key idea is that, let's imagine that I have a lot of classes and I want that the mutants that I sample are equally distributed among the classes. What we are going to do is first split the mutants in different groups. Yeah, for example, the mutants in one class, the mutants in another class, and so on. And then when we're going to sample, we're going to first take one group at random, and then we take one mutant at random from that sample. And that means that when we are going to sample, we are going to get mutants that are equally distributed between the different categories we are sampling. And with this, we have per class, per method, per package. OK? Came back? It is coming back, apparently. I think that I stepped on that. OK, so the next question, so the core idea of this is to make this practical. So OK, we have a way to reduce the number of mutants and get get a good score or representative score by running less time and being more efficient. Now the other question is, OK, when do I stop sampling? Because maybe I don't want to do this analysis where I see for my application when it kind of converges. So what we did to solve this problem, we implemented budgets. OK, so I will tell you about it. You don't need to read it. So what you have is we have budgets to run the analysis. And for example, this budget can be fixed on the number of mutants or a percentage of mutants. So here you can say, OK, run only 30% of mutants or mutations, or run 30 mutations. I don't know. The problem with this is that it really needs to be tweaked really well to work well. So for example, if you have a high percentage or a really high number here, you are not going to win anything in runtime. But if you take too few, maybe it's not a realistic mutation score. So also, there are things that we need a practical thing to run this on a CI. Yes, I want this on a continuous integration environment. So one of the things that we did is, OK, we do the time budget. I give you 5 minutes. Do whatever you can in 5 minutes, and then tell me if this works or not. So we did the GitHub Actions integration. So we have a first version. It can be improved. Always we can improve. It is to integrate this in your continuous integration. It is as easy as just adding these 3 lines here so this couple of lines in a GitHub Action workflow. And then what you get is every time that this runs, it will update a comment in your pull request saying, OK, look, so many mutations were alive, so many were killed, and so on, and it gives you the score. We are going to arrange these to show the details of the mutants, but you get the idea. Of course, sometimes, so this is if you just want to use it out of the box. If you want to go inside and do some fine-tuning of the thing, we have also done a couple of tools. So Paul, that is not here, did this, and Yona was helping using it and tuning it also. So what we have is a mutation matrix and a mutation heat map that show you an overview of how the mutation worked in your project. Yes. So here, for example, what you see in this this table is that we have each kind of mutation here, and then how the test killed this mutation. So, for example, we see that this operator here, this mutation operator, was killed a lot by all the tests almost. Yeah. But there are operators that were never killed. So actually, this guy was just consuming runtime. We created mutants, but no tests were actually killing them. So I don't know. You can fine tune the process doing this. It's good to be a bit resilient with this. So if you want to use it, so I subscribed this morning, Nuri, to the awards. So what I'm going to do, if I win something, I will put it in a pool of money to use it to pay students. Because this is not my work. This is the work of a lot of people. So I will not get the money myself. But if you want to know more, I'm going to show it in the awards this evening. If you want to use it, come talk to me. We can test it. We can see, for example, if you want to have specific operators, or if you want to contribute and add some ideas that you have, come. So just to give a summary, because I'm done with this. So what we did is in the last 6 months, is to make it work between Faro 9 and Faro 12. We did some performance optimizations on the process itself, but also for being usable in many kind of projects, using the ideas of budgets and random sampling. There are also a lot of other features because Paul was working a lot on this. So on logging, test filters, we had new operators that mutated your code and so on. And of course, I am not the main author of this, so I just wanted to share this with the community. So thanks to everybody that participated on this. Thanks. And maybe Ronnie, you want to? Okay. Yes. Questions while Ronnie can probably start.
How do you detect mutant is not covered?
That the mutant is not covered. We use code coverage also. So.
Yep.
But no, so
you create a mutant. And
yes.
You have a new mutant.
Yes.
How do you do the
we don't tell you if it is covered or not. So we just tell you the mutant survived. So.
Yeah, but you said that one approach was to discard mutants
yes.
not covered. So
yes.
you need to know beforehand if a new mutant is covered
so
or not.
You run previously a code coverage, and then once you have the code coverage, you only mutate the code that is covered.
Yeah, but you need a first run.
Yes, I need a first run of
mutants to discard the mutants that are not
but
covered.
It's negligible. So if you look at the amount of time that is going to run to take the analysis, running the test once without any modification of the code, no. So just to get the coverage is negligible. Yeah.
Okay. The other question is, in the first example
yeah.
shown, you change, you put a false, like the mutant was a false in an
yes.
if true
yes.
false. How do you detect that is not a false failure? Because you are, for instance, you said, okay, you have a test that expected the second branch or the first branch, and then it fails. But probably that test was preparing the scenario to cover the first
yes.
branch. So the failure is not a real failure.
No, it's not a test fail. So if the test fails,
yeah.
that means that the mutant was killed and your tests are good. Now, what happens if you do that mutation and then all your tests, they are still green?
All right.
And that's the point. It survived. And okay, you want, so yes, I like the X-Men, but here we want to kill the mutants.
Okay, thank you.
Yeah.
Guille, is there any research about the possibility of a tool that might help you improve the test after you get this data? Let's say I got this mutation on this operand or something, and you know which test make it kill or not kill. So maybe there's a way to say, okay, if you have this test written this way,
So
you can improve it somehow. Improve your test about somehow automatically based on the results.
So, for example, the Mutalk has, but it's not there yet, so it's difficult to really. It was difficult to actually show it. So now that we have this, it's better. Every time that you have a mutant that survives, Mutalk has support to tell you, to give you hints on how would you fix your tests. So, please write a test that covers. But sometimes the mutants. So the thing that the test is complicated to write, so it's difficult to go from the mutant that is failing here to the test. I know that there's people that, for example, have been using the mutation score as a target, so as an objective function for code generation and test generation analysis. So last year, Alexandre Vergel showed a genetic algorithm that generates tests automatically. And if you say, OK, a good generation is a one that improves the mutation score, then, but it's a kind of a brute force analysis. And also, I don't know, for example, there is Gabriel, that I don't know where he is, that he used this to evaluate his test generation approach. So,
Is there a question there?
I needed to.
Hi.
Yes.
If you do a code analysis, you can see what tests correspond to the code coverage, right?
Yes.
So you don't have to mutate code outside of that because
Yes.
you know automatically they
Yes.
will fail.
Now, in practice, just doing a random sample, it's better than doing that. So you at the end, for example, by default, Mutalk doesn't discard the non-cover mutants because just the random sampling tells you so gets rid of, so it kind of subsumes the other optimization. So I know.